Hello, European GNU Radio Days. My name's Hayden Nelson from NI, and thank you for giving us the opportunity to speak and sponsor the event. We sure wish we could be there in person. Today, I have something pretty cool to share with you. We're using this event as the first public announcement of the latest USRP from Ettus Research, the NI Ettus USRP X410, and I have one sitting right here. And so, in this presentation, I wanted to, first start with a brief look back and at software-defined radio technology and how it's evolved within Ettus Research over the past 10 years, and do mostly just a technical deep dive on what's inside this new X410. It's really a first in a series of radios that we'll be coming out with, and it's a new generation of platform. That's why it's the X400 series. If you're familiar, we had the X300 series. This is the first in that generation, is the X410. So, well, let's get started and take a look. All right, so let's have a look. So this is the latest USRP from Ettus Research. And so, I kind of wanted to start with just a look back. We're here in 2021. Last year and a half has been a rough one for us all. But over the past 10 years, so NI actually acquired Ettus Research back in 2010, and most people have known Ettus Research as a big supporter of the open source community. We've been a part of the GNU Radio community for a very, very long time, and we still continue to support and plan to support that activity. As around, the majority of our SDR users are open source users, and so there's no plans for that to change. And it's really interesting to look at, kind of the history here as I went back. I've been with NI since 2009, and I've joined the software-defined radio team in 2018. So there's a lot of great people who are responsible for all this innovation between, since before we acquired it. Of course, Matt Ettus was the inventor of the Universal Software Radio Peripheral, or USRP. And when we acquired Ettus Research in 2010, there was really the USRP 1 and USRP 2, and those were really cool products, really cool radios, but we actually gave the last USRP 1 away at GNU Radio Conference 2018 in Las Vegas. But they were a great radio but it was relatively narrow band and had some limitations to it, and we continued to evolve that over the years, where we around 2011 was the B100 series, and then the E100 series in 2012, which was kind of taking us into this smaller radio size initially, but we found there was a lot of need for folks that wanted to put inline digital signal processing on the FPGA. 2013 was the X300 and X310, and around this same time frame, I was working a lot on FPGA work, and so I found this particularly cool and useful as the X310 series radios, having the ability to program the FPGA, but I always found it relatively cumbersome to have to build everything from scratch. And so we've made a number of improvements, not only on the hardware, but the APIs and frameworks around FPGA over the years. So the X310 was the first radio kind of in this X410 style form factor that was a little bit larger, multi-channel, large FPGAs. It was connected to a host, so you kind of had to have an external computer. That's what it was intended for. It was a radio peripheral. And then it was built modularly with a motherboard and a daughter board. And then as Moore's Law, marched forward, we were able to get, we started with very banded solutions. There was one that went from one frequency to another, narrow band, wide band, and as the chipsets became more and more advanced, we were able to cover all the bands that we wanted with very wide bandwidth, and that was kind of culminating in the UBX and the TwinRX daughter boards that went into the X310. Now, there's a lot of products in between here that I just kind of summarized it here, but the X310 was one of the most popular high-performance radios because of the combination of the RF performance as well as the FPGA performance. And so that led to a lot of cool applications. We saw the Coliseum project that DARPA did a couple of years ago. We have some massive MIMO research test beds that were based on the X310 architecture. And so from that point, we actually had a lot of demand for, chipsets were getting smaller, FPGAs were getting smaller. wireless, analog devices has a lot of great chips that integrate transceivers. So we built several software-defined radios that were smaller size, weight, and power, like the B200 Mini series in 2017 and the rugged E310 12 and 13 series later on in 2016, 2017 time period. So that kind of brought us into this deployable open source software-defined radio that people have been using for a lot of applications. I can't even tell you all of them. Sometimes people don't even tell us what they do with these things, but they're very powerful small radios. I mean, I even have this Velcro on the back of my laptop here. It's because I'll Velcro a B200 Mini on there and just do interesting experiments with it. And so around 2018, actually around when I joined NI, we started investing in higher performance radios because we saw a lot of applications that needed wider bandwidth, multiple channels, phase synchronous applications, and that's where we invested in building on the Zinc platform. So Zinc from Xilinx is this chipset. It's a system on chip that has an FPGA fabric as well as an embedded processor subsystem. And now this gave us the opportunity to have these as somewhat embedded standalone devices. Now the E310s, they also had Zincs, but they weren't particularly very powerful in terms of the FPGA resources, whereas the N310 and the N320 and the N321s had much larger chipsets, more channels, phase synchronous, and they allowed a lot of really cool applications. And then between then, we recognized, hey, with all this FPGA resources, it's kind of like the old hooking up a fire hose to a garden hose. It really put a lot of strain on the FPGA processing resources, and we had been working on something called RF Network on Chip, or RF NOC, which is a FPGA framework for open source that actually plugs into GNU Radio, and we did a lot of enhancements on just the APIs and on the streaming framework and the fabric of the RF Network on Chip framework. And in truth, admittedly, a lot of that was in preparation for the latest USRP, the X410, which we're releasing here in June of 2021. And this has 400 megahertz of bandwidth on it, this radio. So you can imagine that many applications won't be able to offload that data. That's a lot more bandwidth than, say, a B200 Mini, which has 56 megahertz of bandwidth. So it's a lot of data to process. And not only is it a huge bandwidth, there's 4 channels on this. So we had to do a lot of enhancements and improvements to UHD and refactored a lot of code. I spoke about this at GNU Radio Conference 2020. What I neglected to say at that conference was that a lot of that work and upgrades in UHD 4.0 was in preparation for this product. Of course, I couldn't say that at the conference, but that's the reality of the matter. So here we are, June 2021. We got the USRP X410. This is what it looks like. And so some, kind of, I've broken this up in really 2 buckets here, into RF capabilities and into digital capabilities. We'll start on the left with RF capabilities. We've listened to you, and we've seen a lot of applications out there that need to go lower in frequency. On the X310 and N210 products in the past, we had these daughter boards that would go down to really low frequencies, but it became inconvenient if you wanted to have a single radio that covered both of those bands. So this one, we've done our best job to get it to a low frequency at 1 megahertz and a frequency range up to 7.2 gigahertz. Now RF daughter boards on this, we're calling them the ZBX. They're a super heterodyne design. We are evaluating ways to actually even push that a little bit higher, beyond 7.2 gigahertz, but today at release we're speccing it at 7.2 gigahertz. Now the really cool thing is it has 4 channels in, 4 channels out at 400 megahertz of bandwidth each, which is a boatload of data. Now, you don't have to consume all that data on the host. There are onboard digital up conversion and down conversion, and you're able to adjust your sample rate accordingly. But for really wideband applications, specifically around 5G new radio, that has channel bandwidths that are really wide, and that was one of the main applications for this radio, as well as folks in many defense applications that are doing signals intelligence. I have a demo video that will have hopefully posted in our booth we worked with an early customer, 3DB Labs, where they showed off using the X410 with 100 gigabit Ethernet. to use it with their signals intelligence software, taking advantage of that massive 400 megahertz of bandwidth, which I thought was really cool. And it has a pretty high output power. So be careful with great power means you can blow a receiver if you hook it up and loop back. So use attenuators accordingly. And you do notice here I have a little C specifications for details. 22 dBm out. Power tends to be frequency dependent. At higher frequencies, that max power is going to certainly fall off. So I just wanted to add that caveat. And that behavior spans all USRPs if you've worked with them. Now, so the RF capabilities are pretty good, and I'll dive into some deeper specifications later in the presentation. But on the digital capability side, this is based on the Zinc UltraScale Plus RF SoC. And if you're not familiar with that chip, I'll show you a block diagram of it, but it's a really cool piece of technology. And in my mind, I looked at it and said, this is perfect for software-defined radio. It's a single chip. It has a FPGA fabric with a number of IP cores plugged in that you can use, so you don't have to take up programmable logic resources. It has a quad-core application processor, ARM Cortex-A53, and a dual-core ARM real-time processing unit. Has SDFEC, if you're not familiar with that, soft detect forward error correcting code, really important for communications applications. We actually did a communication prototype one time and implemented an SDFEC in FPGA resources, and it took multiple FPGAs. So having that on board is really, really helpful. And so a lot of data coming in on the RF side. How do I get it off if I need to? We have two QSFP28s that are capable of running at 100 gigabit Ethernet. Now, we do plan to release the 100 gigabit Ethernet support in a few months post-release, as well as we have the ability to connect with PCI Express Gen 3 by 8, and that'll be predominantly for our LabVIEW customers using those 8 multi-gigabit transceiver lanes. So an RF SoC has 16 multi-gigabit transceiver lanes, and we kind of split it, 8 for the QSFP 28s and 8 for the PCI Express Gen 3 by 8. And so it does have the standard things you've come to expect on USRPs in terms of synchronization, 10 megahertz, PPS, GPSDO, triggers, etc. And we will be supporting both GNU Radio UHD RF NOC on this naturally. I know it has an NI brand on it, and many people have associated NI as like that's the LabVIEW brand. Well, NI's changed a lot over the past 3-4 years, and we are really diving into supporting open source options, across beyond just USRPs. We will obviously still support LabVIEW, but this is a device that supports both LabVIEW and open source. And so, I guess just to reinforce that is on the FPGA side, we are supporting LabVIEW and GNU Radio UHD. That includes all the C++ and Python APIs, and so everything you've come to expect with an X310, those APIs will work. In fact, when 3DB Labs used this, they just recompiled with the latest USRP hardware driver. We had to, for those of you you're looking at a repository, you've probably got a preview of this because we had to push it a little bit ahead of the release, and but we gave our early access customers access to a private repository where they just rebuilt it and used standard API hooks that they had in their Scepter software, and they were able just to plug it in. Of course, changing parameters specific to this radio enabling it to run at a much higher bandwidth. We will support all the Xilinx tools like Vivado and specifically in the context of RF network on chip on this particular radio. And so here's how it kind of stacks up. I have sort of two views on how it stacks up against the various other radios, but you can see it all the way over here on the right. It's considerably lower frequency and higher frequency than all the other radios in the portfolio. Wider bandwidth, more channels. So it's about double the bandwidth of our widest bandwidth radio, double the channels of that radio, and has double the FPGA resources of those radios. So you're getting a lot more performance out of this, and it has things like 100 gigabit Ethernet. Now, one thing you'll notice that's lacking on this radio is local oscillator export. So if you're familiar with the N320 series radio, so for people needing to do local oscillator synchronization, say you have, 32 radios and, well, however many, typically a power of 2, you're going to want to synchronize those through a 10 megahertz PPS, so all the clocks are based off of a common frequency reference. So everybody's sampling at the exact same frequency. And another part of synchronization is local oscillator synchronization. Now you'll notice this radio doesn't have any local oscillator exports. We'll go into the front panels, and it's not really intended for that. There's ways you can get there with synchronizing oscillators and resetting them synchronously, but it doesn't have that same level of phase synchronous. It was a trade-off to try to not make the product too expensive to price it out of certain applications. And here it is kind of at the top of the performance chart here. This is a view if you want to get a breakdown of the different classes of product. I kind of break it into 4 models: the standalone, embedded, or high performance FPGAs, which are on that kind of top green stripe. The X310s, that's sort of the host connected, requiring either 10 gigabit Ethernet or PCI Express. And it's both NI and Ettus Research branded model numbers. But the X410, we decided to kind of drop that and have just one model number and not confuse people, because X310s, we had certain daughter boards built in the most popular way, and then we gave it an NI model number, which made sense at the time. We wanted to simplify that complexity of the USRP portfolio starting with the X410. Compared to some of the lower end, lower swap radios down at the bottom. So it is kind of the Lamborghini, if you will, of our USRPs. We've tended to invest at the high end lately of higher performance radios for those higher end applications. In the past few years, and that's evident by this X410 radio. And so here is a lot of detail here, and so let's dive into this. And so again, I've broken the product up, like what's inside this little thing here, and gives you a little bit more detail into what's inside the X410. And as you can see, I started looking at the block diagram of the RF design and wanted to try to show you that. It's a little more complicated than I wanted to put on a PowerPoint slide here. But ultimately, we have 2 daughter boards in this radio. So, and I will caution that in the X310 series we had it where you could interchange the daughter boards. We don't plan to do that with the X410. We didn't do that with the N320 or the N310 series because as these radios have gotten more high performance, assembling them and testing them as a unit has made a lot more sense for our customers to make sure that they don't run into any issues. So it has 2 daughter boards and it has 2 signal paths per daughter board. So it's a pretty dense daughter board in terms of RF componentry on it. It does have a lot of filters on the RF side past the last mixer, and that is selectable based on the frequency, so you don't get a lot of image rejection or images in your signal going in or out. A lot of this is set through whenever you're choosing the gain. So we don't give you access to control each of these individual components. You're going to just set a gain, and the driver will take care of some of that complexity for you. But at least you can see that it is a super heterodyne two-stage up conversion. Now that is frequency dependent. Once you get up to the higher frequencies, there's some bypass paths, in the signal chain that will bypass that first mixer. And that'll be all abstracted to you, but I just wanted to kind of show you that within this little box you have 4 signal chains, really 8 because you have 1 up and 1 down on each section of the signal chain, and it gives you the option to, similar to other USRPs, you have a TX-RX port that can act as a transmit and receive, and a single port that acts only as a receive. So you have that option to have a single antenna that can act as a transmitter then a receiver through a switch, or one is a transmit and one is a receive. And those are kind of the 2 modes of operation you can run the RF section. And it does come by default with a GPS discipline oscillator. If you're not familiar with what that is, you hook up a GPS antenna, synchronizes to the very stable rubidium clocks on GPS and gives you a nice stable reference. And that's important if you're trying to synchronize multiple radios in terms of say a time division of arrival type application. And it gives you a lot of synchronization and stability through the GPS signals. Now, so you got 2 daughter boards, and each one there's 4 channels coming off of this. And on the FPGA side, so that routes through the connector, the analog goes through the connector, the FPGA is on the motherboard of the X410, excuse me. And if you're familiar with the Xilinx RF SoC, it actually has 8 channels on it, and you're noticing we only have 4 transmit and 4 receive channels. You're like, hey, where'd the other 4 go? Well, we just didn't use them. It would have made the product way more expensive, and we would have had to make it twice as tall, and we just didn't really see a need to use all 8 channels on the RF SoC. So 4 of them are not even used. And so we're using 4 DACs, 4 ADCs in kind of a 4-channel mode. And these DACs and ADCs are pretty high speed. We're sampling, they can go up to 3 or gigasamples per second and even higher. And so you're producing a lot of data. And within that data, you may not be interested in all the bandwidth. And so there are built-in digital up converters or digital down converters, which allows you to kind of retune within the band. So you can kind of see that here within the IP. Here, let me pull up a laser pointer here. So you can see here's the DACs, here are the ADCs for one half of the daughter board. I've kind of stacked them here. There's one behind this because I didn't want to make this block diagram too complicated. The SD FEC in the FPGA logic, so this section here is the FPGA logic. And within there you have this, I think you have 8 of these SD FEC cores, one per channel. And you do have a pretty, it's a small block here, but you'd have a pretty large FPGA logic block. And you have digital up converters, down converters, SD. You can see here DDC is digital down conversion for the A to Ds. And so you don't have to build your own DDCs and DUCs in FPGA logic. There's IP cores already built into it. And within the FPGA fabric, you have some high-speed serial. Now this is a little tiny block, but it's an important piece of this is because you're going to need a lot of bandwidth for offload. So we have 2. Like I said, this thing has 16 multi-gigabit transceivers coming off of the chip. We've taken 8 of them, running them into 2 QSFP28s and one to, and we'll call an iPass. 2 of them you can run that for PCI Express Gen 3x8. And so we also took some of the GPIO and we run it to an HDMI connector. You can see 2 of them right here on the front of the radio here in my little. And I'll show you a close-up image of the front panel. Now inside the embedded, so that's just the FPGA section of the chip. On the embedded CPU section, you have 2 kind of CPU processing subsystem. One's a quad-core for ARM for application processing unit. One of them's an RPU, which is more for like monitoring control, things like that. And it's an ARM A5, and there's 2 of those. Has built-in DDR controllers and interfacing. So, communicating with this thing, we have several, a 1 gigabit Ethernet port, USB ports, JTAG for programming the FPGA, controlling fans. And one of the really cool things about this chip is for certain applications that need encrypted security, it has like a security management unit within the FPGA as well. So there's a lot of technology baked into this thing. And you can imagine that, hey, I can run this thing as a inline signal processing repeater for certain applications, maybe communications, EW, maybe even some radar applications. The lack of synchronized channels limits some of the radar functionality that you could do with this, but single channel, it should be fine. Communications applications for doing filtering, FFTs, decoding on the FPGA. There's a lot of performance that you can get out of this FPGA logic and the onboard signal processor. Say you wanted to deploy this into a area that you don't have a computer next to it. Well, if your application can run on this ARM A53, which is pretty powerful little embedded processor, you could potentially do that. So it kind of combines the N320 series with the X310 series. All right, so here's some of the radio characteristics here. It's a little bit small text, but 4 channels. We've already said 20. You can only be careful. Don't put more than 20 dBm into it. You'll damage it. The performance of this is not a calibrated instrument. We have done our best to clean up the spectrum, get good spurs out of it. But whenever you have a wider bandwidth, you have more opportunity for images seeking in. with more bandwidth becomes the potential for more noise in band and things of that nature. But we've done, I think, a pretty good job of getting a reasonably good noise figure and spurious performance on this radio. And so here's what it looks like on the front panel. I already mentioned, you can kind of see these daughter boards again. They're not interchangeable. You kind of got 4 channels, receive and transmit, so thus 8 connectors on the front. These are those 2 GPIOs, so you actually have 2 of those on the front for synchronizing with another radio. You can program the FPGA, do whatever you want with these things. It's a standard HDMI connector. And on the back, you can see those at QSFP 28 ports for dual 100 gigabit Ethernet, all your referencing GPS, PPS. This is for PCI Express Gen 3x8. One of the really cool features of this that is different than the X310 and the N320, I know this is kind of a silly thing, but is the thermal performance of it. On the X310, it came in the sides and out the back, which made it awkward sometimes to rack mount these in a large configuration. You had to leave a little bit of space between them. On the N320s, the air came in from the side and vented out the side, so you had to also leave space if you wanted to rack them together. And one on the right would blow hot air into the one on the left. And usually it wasn't a problem if you just gave them enough space and ventilation, whereas the X410, it vents in the front and out the back, and vice versa. And you'll notice there's some screws here that you can actually buy an accessory fan module that'll invert the airflow, and so you can either have it flowing from front to back. So if you're going to mount this, say, next to like a server and you're trying to manage airflow in a larger system, you have options to control the way that your thermal performance is to keep the radio at a constant stable temperature for your application. So that's a new feature of the X410 is some thermal performance. And then just your standard power and consoles and Ethernet ports for command and control. Well, that's it. That's the overview of the latest USRP from Ettus Research, the NI Ettus USRP X410. Hopefully that was useful to you to understand kind of what's inside this thing. Now, if you have questions, feel free to reach out, and you can learn more about this radio and our other radios at ni.com/SDR, or just go to ettus.com and hit the Contact Us button, and we'll be happy to connect for a conversation and talk about your SDR needs. I appreciate your attention. See you next year, hopefully in person. Thank you very much.